second week of the summer classes. I have listed or posted on the classes webpage links to recordings to Illinois media space of the 3 previous lectures, so you can access them through the webpage. I also have recordings scheduled to appear on YouTube. Somehow we lost the video. Okay, we have different Zoom camera here available to us when one of them doesn't work. Luckily, we have backups. What we'd like to cover today is having covered the first realization of nuclear energy in the modern age on the first reactor, and then the use of nuclear energy for on the bombings of Hiroshima and Nagasaki in Japan. We expanded it to look at what is the present state of affairs in terms of the nuclear world. To gain a quantitative knowledge of the situation, we would like to look at what are the underlying forces of nature that govern it. So today, we deal with 3 of the 4 forces of nature that are postulated to have existed at the time of the Big Bang. This is the state of knowledge, is that at the time of the Big Bang, 4 forces of nature were combined together and they separated at that time. Whether knowledge and science will change that in the future is speculative, but the 4 forces under consideration are the strong force. The strong force exhibits itself in the force that binds the nuclei together. And so this is what we'll start by covering today. But the second force is the opposite of the strong force. It's designated as the weak force. The weak force exhibits itself primarily in the process of radioactivity, where nuclei emit different forms of radiation to try to reach a stable configuration. The third force of nature is the electromagnetic force, which exhibits itself in the electromagnetic spectrum, from light to X-rays to gamma rays to microwaves, where the energy is transmitted with 2 perpendicular waves, one electric and one magnetic. That's why we call it the electromagnetic force. We're not going to delve deep into that particular force, but we are interested definitely in the emissions of gamma radiations and X-rays, which are part of the electromagnetic spectrum that are associated with atomic phenomena and nuclear phenomena. The fourth force of nature is the electromagnetic force, and we leave this to your other classes. So we will delve into 3 of the 3 main forces of nature in our class. So without going further, we are going now to consider the strong force for today. This is the links in the web page. This is the media space of the first lecture, second lecture, and third lecture. I already posted them on YouTube, and you will see that shown posted maybe this afternoon or tomorrow. All right, so let's start by looking at our web page here, and we go to our web text and identify where is the strong force. So here we have nuclear processes, the strong force. Later on, when we'll deal with radioactive transformations, that would be the weak force. And when we deal with gamma rays interaction with matter, that would be the electromagnetic force. Oh, we are going to leave the gravitational force to your other classes. But look here, we are going to take the challenge of covering 3 out of the 4 forces of nature. So we'll start here with the nuclear processes, the strong force. That makes us more quantitative in the treatment of the information that we covered in the previous 2 chapters. The first important aspect of the strong force is to compare it to chemical reactions. And nuclear reactions are reactions that occur in between the nuclei, whereas chemical reactions are reactions, as we all know, that occur in between the atoms. So for instance, if you burn coal or you oxidize it, carbon combines with oxygen as a molecule and gives us carbon dioxide. We all know that. Water is formed by the combination of hydrogen and oxygen, and 2 molecules of hydrogen combined with 1 molecule of oxygen gives us 2 molecules of H2O, which is water. In nuclear applications, we can treat uranium dioxide, as we'll see later, with hydrofluoric acid, and we get water plus uranium tetrafluoride, or UF4. The energies involved in that type of a reaction are typically in the electron volt range. So burning coal, or the energy released in, let's say, fire, is in the range of 4 electron volt. The ionization energy of the hydrogen atom is 13.6 electron volt. Remember these 2 numbers, 4 and 13.6 electron volt, because we'll compare that later on to the energy release from nuclear reactions. And I'll give you a hint here. They're not going to be in the electron volt range. Each reaction would be in the million electron volts. So a factor of 1 million difference in the energy release between chemical reactions shown here and nuclear reactions. Another interesting aspect of chemical reactions that we can observe is that the atoms preserves their nature. The carbon in the reactants remains as carbon in the products. The hydrogen in the reactant remains as hydrogen in the products. Not so, you'll find that in nuclear reactions, the identity, the chemical identity of the reactants and the products can be very different. Hence, transmutations occur, and that was the dream of the alchemists in the Middle Ages. Isaac Newton himself was considered as an alchemist, and the dream of the alchemist was to turn the transition elements like lead or copper into gold. They promised it to the princes and the kings, and when they failed, they lost their heads because they were paid to do that and failed miserably. Today, in nuclear reactors and particle accelerators, the transmutation of the element is a routine type of a process in general. Again, we are dealing with the units used in these nuclear reactions, the electron volt, which is the energy, kinetic energy acquired by an electron when it falls maybe in a condenser between the 2 plates of a condenser through a potential drop of 1 volt. You can basically express that electron volt in British thermal units, or in kilowatt hours, or in the joule, other units of energy. The electron volt is a very small unit of energy, so usually we adopt the kilo electron volt, which would be a kilo in Greek. The Greek prefix is 1,000, and million, of course, is 1 million electron volts. So we designate it as the MeV, or the million electron volt in those reactions. Again, each atom participates as a whole. The resulting products are different from those entering the reactions as reactants. A sharing of exchange of electrons occurs. So the reactions there in chemistry occurs in between the electrons around the nucleus of the atoms. The nuclei in chemical reactions are somehow unaffected in general. Nuclear reactions are different. By definition, they occur in between the nuclei of the atoms. In that case, we can get transmutations. For instance, you'll find that the isotope of aluminum, aluminum 27, notice that's the notation here is a chemical name of the element, aluminum. 13, its atomic number, the number of electrons or the number of protons for that isotope, and 27 is the total number of nucleons in the nucleon of the isotope of aluminum, aluminum 27. You'll find if you bombard aluminum with particles emitted from radioactive substances emitting helium nuclei or alpha particles, as we call them, you'll find that the transmutation occurs. You end up with a proton or a nucleus of hydrogen being emitted, and that aluminum 27 turns into silicon 30. So there is a change in the nature of the elements because the reactions are occurring within the nucleus itself. If you bombard nitrogen, remember that we are primarily breathing nitrogen. 70% of the air we breathe is nitrogen, 15% only is oxygen. If you bombard that nitrogen with alpha particles also, and these are two of the first reactions ever discovered in the study of nuclear phenomena, you end up with hydrogen being released here, one proton, and the nitrogen 14 becomes an isotope of oxygen, oxygen 17. So in general, the isotopes are described as X, the name of the chemical name of the element, like aluminum or nitrogen. Z1 is the atomic number, and A1, this would be the mass number, the total number of nucleons in the nucleus, the number, which is the number of protons plus the number of the neutrons. If you subtract 13 from 27, you get the number of neutrons in the nucleus itself. Each one of those reactions, as you could see here, is associated with a very tiny change in energy in between the reactants and the products of the reaction. That change in mass, according to Einstein's equation, is exhibited as kinetic energy of the reactants if of the products if the reactants were initially at rest or had zero kinetic energy. The change in mass in chemical reactions is very, very, very small, but it is much, much larger, as we'll see in nuclear reactions. Several laws apply when we balance those reactions in a way somehow different than what we do in chemical reactions. You'll find that first, the charge is conserved. So charge here is 13, the number of protons or number of electrons, plus 2. You'll find that 13 plus 2 should be equal to 14 plus 1 in the products. Here, 7 plus 2 in the reactants is also equal to 8 plus 1 in the product. So charge is conserved. Another conservation law applies here, which is the conservation of the total number of nucleons. So you have 27 here, protons plus neutrons in the aluminum combined with 4. You'll find that in the products, 30 plus 1 should be equal to 27 plus 4. Here, 14 plus 4 should be equal to 17 plus 1. So here we are conserving the charge and we are conserving the nucleons so that we can establish the relationship between the reactants and the products. Another important quantity that is conserved in nuclear reactions is the mass is conserved. The total mass of the reactants here should be equal to the total mass of the products, except that some part of the mass, that delta M, according to Einstein's equation, is turned into kinetic energy of the products. Those products of the reaction interact with the surrounding atoms and molecules, and lose their kinetic energy as molecular vibrations, which we sense as heat production if the reaction is exothermic. So the conservation laws that we observe here in the exhibition of the strong force is that Z1 plus Z2 in the reactant should be equal to Z3 plus Z4 in the products. A1 plus A2, which is the mass numbers of the reactant, should be equal to the mass numbers in the products. And then the delta M that we wrote for the equation should be equal of the mass of the reactants minus the mass of the products. And there are another property other properties that we are going to deal with later on is momentum also is conserved, not just total energy, and another quantity that we call parity associated with the conservation of momentum. All right, we want to become quantitative, so that difference in mass should be measured. And we take in that case a reference, carbon. If you go to the library, you'll find that very old textbook considered oxygen 16 as the reference, like the meter is used for measuring distances. That is some kind of a scale. So we take the 1/12, the mass of the carbon 12, in that case, neutral atom, divided into 12, and we call this the atomic mass unit. In all the older specific scientific paper reports, the oxygen 16 isotope was considered. It gives us a slight difference in the masses that are measured and published in general. If we want, if we take 1/12 of the mass of the carbon 12 isotope, so the mass of the carbon 12 isotope basically would be exactly 12 atomic mass units. In the reactions that we wrote earlier for aluminum, silicon, and nitrogen, you go to the chart of the nuclides, and you find that the mass of the aluminum 27 measured on a mass spectrograph is 26.981541 atomic mass units. So the 27 here, the mass number is really the rounding of the actual atomic mass of the in that case, we are talking about the nucleus here. Later on, we'll consider the neutral atom, which would be the nucleus plus the electrons surrounding it. The helium-4 nucleus is 4 atomic mass units, 4.002. And we tried to take as many decimal points here for a reason that will become clear later, because the changes in those masses are measured at the 3rd decimal point. You'll find that later on, 1 atomic mass unit is approximately 1,000. 1 atomic mass unit is equivalent to 1,000 million electron volts. So in that case, we need to take as many decimal points as we can. Otherwise, we lose resolution. We cannot just take in the measurement of the delta M's or changes in masses the roundup of the units. So let us go to the 2 reactions that we wrote earlier as an example for measuring the delta M. We define the delta M, or the mass, the change in mass in nuclear reactions, as the mass of the reactants minus the mass of the products. In the first reactions, where an alpha particle interacts with aluminum 27, that would be the mass of the aluminum 27 minus the mass of the alpha particle plus the mass of the alpha particle as reactants minus the mass of the product silicon 30 and the mass of the proton or the hydrogen nucleus in that case. Notice that we are using the nuclear masses right here. Later on, we will distinguish between them and the neutral atoms, but for the time being, we can go now to the chart of the nuclides. The mass of the aluminum 27 has been listed right here from the chart of the nuclides. We substitute the numbers, we add the masses of the reactants minus the masses of the products, and you find that you get a positive number, and the difference is 2.5 at the 3rd decimal point in atomic mass units. If you consider the other reactions where an alpha particle interacts with nitrogen, we can also calculate the delta M. The delta M would be the mass of the nitrogen 14 plus the alpha particle minus the oxygen 17 and the proton. And when we add those numbers and subtract, we get a difference in the mass as 0.001 1,000th of an atomic mass unit. But it is negative, meaning that the masses of the products are larger than the masses of the reactant. So that reaction here gives me a positive value of the mass of the reactants minus the mass of the products. And that positive difference in the mass is converted into kinetic energy of the product. So energy is released in the process. We designate as that type of a reaction with a positive difference in mass between the reactants and the products as an exothermic reaction. For this reaction here, the reaction is not going to proceed unless we provide it with a minimum amount of energy equivalent to that 0.001 atomic mass unit of energy. So in that case, because the reaction is absorbing energy, needs energy to proceed from left to right, we call this an endothermic reaction. So the difference in mass is positive in the first case, negative in the first case. Now, this terminology is a terminology adopted in nuclear and radiochemistry. So that's nuclear chemistry that we are doing right here. And it's in exact opposition to what happens in conventional chemistry. So this reaction, we call it exothermic because energy is released. We call this endothermic because energy is absorbed or is needed to drive the reaction from left to right. And in chemical reactions in general, I warn you, for the chemical engineers, our friends here, that it is the exact opposite as a terminology. Now, so we know now that there is a mass difference in the case of nuclear reactions or the strong force that keeps the nuclei together. Now, we want to quantify this, so we have to invoke a law of nature that you have read about in the case of in your classes on physical chemistry, and this is designated Avogadro's law. We wanted or needed to convert the atomic mass units into units of grams and be able later on to use Einstein equation to convert that into units of energy. So we want to establish an equivalence between the delta M, the change in mass, and the energy release, where the change in mass is multiplied by the square of the speed of light, and then we find that we have units of energy. Avogadro's law in physical chemistry says that the number of atoms or molecules in a mole is defined as the gram molecular weight of any substance. It's the amount of the substance having a mass in grams equal to the atomic or molecular weight of the substance. So the number of atoms or molecules in a mole is a constant of nature designated as Avogadro's number. It's 0.610 to the 24th atoms or molecules per mole. I'm choosing by 0.610 to the 24 for a reason that will become clear later on, that 10 to the plus 24 cancels with a unit of the Barn for cross sections, which is 10 to the minus 24. So it makes our calculations easier later on. In the textbooks, you'll find it listed as 6, 10 to the 23rd power, which is the same in that case. Coming back to the carbon-12, 1 gram molecular weight or 1 mole of carbon-12 would be equal in that case to 12 grams of the carbon-12 isotope. If you take 48 grams, that would be 48 divided into 12. This is the number of moles now. That would be 4 moles of carbon-12. So to calculate the number of moles, we take the mass of the substance in grams that we are dealing with, divided it into the molecular or the atomic. To be exact, you should really use the atomic weight itself, 12.001, the decimal point. But for simplification here, we are taking it as an approximation. 48 divided into 12, 48 grams of carbon-12 contain 4 moles of the carbon-12 isotope. So in that case, the number of moles is defined always as the mass of the isotope divided into its molecular weight. As an approximation, we can divide into the number, the mass number of the isotope. For instance, if you have 64 grams of oxygen, you have two molecules, two atoms of oxygen in the molecule, 16 plus 16. And if you have 64 grams, 64 divided into 32, you have 2 moles or 2 gram molecular weights of that oxygen. Now, since 1 gram molecules contains Avogadro's number in atoms or molecules, and 1 gram mole of carbon-12 has a mass of 12 gram and contains N sub A atoms, then the mass of 1 atom of carbon-12 is 12 divided into Avogadro's number, 12 the atomic mass unit divided 0.6 10 to the 24th. We can deduce that the mass of 1 atom of carbon-12 is 1.99 10 to the minus 23rd gram. We don't have scales that can measure such a small quantity of mass here or weight. In that case, you'll find that we are using our intellect or our knowledge to calculate the mass of 1 atom of carbon-12, 1.99 10 to the minus 23 gram. And this helps us establish the value of the atomic mass units in grams, because here 1 atomic mass unit, as we said, is 1/12 of the mass of the carbon-12 isotope, and the mass of the carbon-12 isotope is 10 to the minus 23 grams, 1.9 10 to the minus 23rd gram. So he takes this number, divide into 12, and we establish here the equivalence between 1 atomic mass unit and the unit in grams. This is using the conventional system of units, or the centimeter, gram, and second system of units. Now, Avogadro's law now allows us to estimate the number of nuclei, atoms, or molecules, depending on the context, in a given gram mass in grams of a substance. If you go back to Avogadro's law, the number of moles is the mass that we have at hand divided into the molecular weight multiplied into Avogadro's number. So if you are interested, instead of the number of nuclei, atoms, or molecules of unit volume, we divide that G here into the volume, and that gives us the density. So here we have at hand 2 forms of Avogadro's law: the conventional form that we find in the textbooks on physical chemistry, and the number density, or the number of nuclei per gram mole, that we find in a given volume. So if we use the density of the material, we get the number density, or the number of molecules or atoms in 1 centimeter cube. With that background from physical chemistry on Avogadro's law, we can establish the mass and energy equivalence. We can turn the delta M in those 2 equations that we wrote earlier into an energy release in the nuclear reactions. Remember, in chemistry, the change in mass is equivalent to 4 electron volts, or 13.6 electron volt for the ionization energy of the hydrogen atom. Ionization energy means that the energy it takes to separate the electron from the nucleus in the atom, and in that case, the nucleus becomes positive, so it is ionized and it has now a positive charge. We go to the very known equation from Mr. Einstein, who established for us that a mass M can be transformed into energy, and the units of energy in the CGS, or the conventional system of units, is ergs. And we must learn how to convert from ergs to BTU to joules. So that's a skill that all engineers must have. So let us acquire it together. So if you have the mass in grams multiplied by the square of the speed of light, you get unit of energy in ergs. And we said earlier in the previous chapter that this is the energy in a given mass, but you'll find that that energy also can be in part of the electromagnetic spectrum, in the photon. So if you have a photon of X-rays, gamma rays, or light, microwaves, radio waves. The energy content is a constant of nature again, that's called Planck's constant. It has units of erg/second multiplied into the frequency of the radiation. So if you, again, as I gave it to you as an assignment, equate the two together, you find some interesting, intriguing equation that relates mass to the frequency of the electromagnetic radiation. So here, this allows us to give a clue on the what you have heard about as dark energy and black matter, and dark matter and black energy in the universe. And this is not pie in the sky, this is real. So this is an actual experiment here showing that it is not just that mass can be turned into energy or electromagnetic radiation, but electromagnetic radiation or the reverse of the process can also be observed in the lab. So this is an instrument that is called a cloud chamber. What it consists here is a cylinder here, as you could see, set on a table, on a pad maybe, with a liquid like alcohol that has a high that can allow the particles to condense. So it would have a the passes of the radiation to create condensation cloud, the same as you could see by sunset. When you look at sunset at the sky, high in the sky, you see planes that are generating condensation trails. The condensation trails come in from the exhaust, from the engines of the plane as water, burning kerosene in that case, that's their fuel. And as it condenses at high altitude, we call this a condensation trail. So if you get a saturated vapor of any material, simply alcohol maybe, you'll find that when you have radioactive substances creating particles, they create condensation trails or contrails in general. Now what we have here is a magnetic field perpendicular to the page of the sheet here. And one property of the interaction of charged particles with a magnetic field is that in a magnetic field, the charged particle rotates around the magnetic field lines. So here is a particle that rotates in this direction around a perpendicular magnetic field to the page. And there is another particle here that moves in the opposite direction. And what are those particles? These are particles that have been emitted or generated by the interaction of a gamma photon, electromagnetic radiation, part of the electromagnetic spectrum. And two masses have been created, really, because that's what is shown here, the condensation trail of one mass moving in this direction, one mass is moving in the opposite direction. The explanation for this is that a photon of gamma radiation, of electromagnetic radiation, has turned in the vicinity of a nucleus when its energy was higher than the masses of an electron and its antimatter, the positron, to be created. The electron rotates in this direction around the magnetic field line. It's a negative particle by definition. And the positron, the antimatter, is a positive electron. It rotates in the opposite direction. So that diagram here, that actual picture in a cloud chamber, shows us that not only can we transform mass into energy, but energy can be transformed into mass. So that's a way of maybe explaining the presence of dark matter. I'll come back to that topic at the end of the lecture. I gave you as an assignment to establish a relationship between a mass and the frequency of radiation, and that defines for us a new constant of nature, which is a Planck's constant divided into the square of the speed of light. The point I'm making here is that in the same way that we can transform mass into energy, we can do the opposite too. We can transform energy from the frequency here in the equation H is Planck's constant. Nu is the radiation, which is equal to the speed of light divided into the wavelength. So energy can go either way, from mass to radiation and from radiation to mass, and that's an established fact in nature. Now let's go back to the Avogadro's law and use a very famous equation by Einstein that delta M in the two nuclear reactions that we wrote earlier, that delta M exhibits itself as energy as released by the nuclear reaction. Now, if you take the change in mass of 1 gram of matter, let's take 1 gram here for delta M, you multiply it by the square of the speed of light, exactly it's 2.99 10 to the 10th centimeter per second, and then you square it, you find that you get 8.9 10 to the 20th power in ergs. And there is a transformation of ergs into joules, is that 1 joule is 10 million ergs or 10 to the 7 ergs. So in that case, the 1 gram of matter releases for us a tremendous amount of energy in joules. Ergs is the energy unit in the CGS system or the conventional system of units. And the SI system of units has joules as unit of energy. And the relationship between them is 10 million ergs per joule. So this is a substantial amount of energy. That's equal to 25 million kilowatt hour of energy like we use in our homes and our businesses in general. Now, coming back to the mass of the positron and the electron in the cloud chamber, we know that the mass of the electron is 10 to the minus 28 grams, calculated from mass spectrographs and the mass spectroscope. You can calculate the energy equivalent of that mass of the electron. So instead of taking 1 gram in Einstein equation, we take the mass of the electron multiplied into the square of the speed of light. That gives us 8 10 to the minus 7 ergs. We turn the ergs into joules, that's 10 to the minus 14. And there is a relationship between the joule and our favorite units in nuclear and radiochemistry. In our case, that is that 1 joule is 1.6 10 to the minus 13 million electron volts. So we establish here that the energy content or the mass equivalent energy of an electron or a positron, the antimatter of the electron, is 0.51 million electron volt. So this, we use the definition of the electron volt as the kinetic energy of an electron charge, 1.6 10 to the minus 19 coulomb, accelerated through 1 volt of potential drop. And we defined earlier the atomic mass units as 1.66 10 to the minus 24 grams. So the energy equivalent of 1 atomic mass unit is 1.66 10 to the minus 24 gram divided into that 9.1 10 to the minus 28 mass for 1 single electron, and multiplied by the 0.51 value of the mass of the electron. And that gives us basically that 1 atomic mass unit, if you cancel the numbers here, is equivalent to 931.48 million electron volts. So a change in mass of 1 atomic mass unit is about 1,000 million electron volts of energy. And there, having established that relationship, then we can take those delta M's in the reactions that we wrote earlier and turn them into energy release. To be able to do this, we have to think about how the strong force exhibits itself in nuclei, how the nuclei in the nucleus are bound together. Why are we interested in this? Because by separating the nuclei from each other, that kinetic energy can be released. We call the process a process of fission. But it also occurs in nuclear reactions. And the opposite process, when you fuse the nuclei together, is what we call fusion. You'll find that there is also a delta M or a change in mass, and this is what we call fusion reactions. So what is the binding energy that keeps the nuclei together? So let's write an equation for it. The binding energy should be equal to the number of protons multiplied by the mass of the proton in the nucleus, plus the number of neutrons multiplied by the mass of the neutrons in the nucleus, minus the actual mass that we measure on a mass spectrograph for that nucleus. Now, the reaction here should be in between in the nuclei itself, in the nucleus, not the neutral atoms. However, if you have gone already to the chart of the nuclides in one of the assignments, you'll find that the data that are given to you are the masses of the neutral atoms. So this is the mass of the proton in the nucleus plus the mass of the electron. So if you add Z, the mass of Z electrons, Z multiplied into ME, and then subtract here from the mass, atomic mass itself of the neutral atom, which is M sub A plus the mass of the electrons, you'll find that Zm plus Zme and minus Zme cancel out, and we are entitled to use the masses of the neutral atoms because the masses of the electrons cancel out. Remember, the chart of the nuclides gives us the masses of the neutral atom, meaning that's the mass of the nucleus plus the mass of the electron. So if we take Z for the number of protons, multiply them by the mass of the hydrogen, one hydrogen atom, plus the mass of the neutrons by the mass of the neutron. You can get this from the handbook of physics, of chemistry and physics, minus the actual mass of the nucleus itself. Then we can get what is the binding energy that keeps the nuclei together. Of interest to us, how much is that binding energy per nucleon, per neutron or proton in the nucleus? So we can take those numbers here from the chart of the nuclides and plot them into that curve that we are showing right here. So this is now the binding energy E sub B per nucleon or per atom or per neutron or proton in the nuclei. And if we plot this binding energy per nucleon against A, the mass number, you'll find that we get an interesting graph. Each point there is one of the isotopes of the elements that occur in nature. We see here that for elements like deuterium and lithium, or A is very small, that binding energy per nucleon is very, very small. For per nucleon for the deuterium, an isotope of hydrogen is only 1.1 million electron volt. As we increase in the mass number, you find that the curve increases, the binding energy per nucleon increases, reaches a peak here around the mass number of iron and nickel, and then decreases with some local maxima and local minima in the graph when we reach the heavy elements like uranium and thorium. And in between the heavy elements that occur in nature, the isotopes of uranium and thorium, you find that there is an empty space. So this area here is considered as an island of stability where the heavy elements are stable. The most stable elements in nature definitely would be around that peak here, which would be iron and nickel. And we all know that the core of the Earth is iron and nickel. So in fact, iron and nickel are very stable elements because they have the largest binding energy per nucleon. Now, if you go to some of those elements with the low binding energy per nucleon, like uranium and thorium, and you split them or fission them using terminology from biology, like in a cell fissions or fuses. If you fission them, you move from that area of that low binding energy per nucleon into the area in the middle of the periodic table of the elements with elements with a high binding energy per nucleon. In that case, the difference in energy is the difference in mass per nucleon is exhibited as kinetic energy of the nuclei, and we call that process a process of fission. So when we decrease the atomic number, the binding energy per nucleon increases, the difference in masses is released as kinetic energy. We call that fission. On the other hand, we can do the same thing by fusing nuclei together, like deuterium plus deuterium or deuterium plus tritium, and we get helium-4, which is also a more stable isotope than what we started with. Energy also in that case is released from the binding of the nuclei together. We call that process fusion. And that curve is named the curve of binding energy because it displays really how much energy is available to us as the strong force. Remember, our chapter is on the strong force. The average for all nuclei in nature is 8.5 million electron volt per nucleon, but you could see here that it can be much smaller in the island of stability where the nuclei of uranium and thorium occur. So we use that to our advantage in the fission process, or in deuterium and tritium and lithium. And in that case, we can use it to our advantage in the fusion process. So this is, in essence, how fission and fusion occurs. What we do is change the amount of binding energy from one nucleus to another. And what is released in that case is kinetic energy. And then we call one of them fission and we call the other one fusion. To display this in more detail, we like to use what's called the mass defect delta, which is the actual mass of the atom minus its the number of nucleons and protons, which is the mass number. And then again, do it per nucleon. So we take that mass defect per nucleon, we call it the packing fraction. And if you go to our appendices in the lecture notes, and you can get those numbers and plot them in Excel and show that packing fraction for the existing isotopes that we know in nature, you'll find that basically you reach a minimum here, which is the inverse of the binding curve. This is a graph I generated myself. And we have here 1, 2, 3, 4 elements that occur in nature. And these are the 3 isotopes of uranium, uranium-234, uranium-235, uranium-238, and thorium-232 as a small island where the binding and the packing fraction is the largest in general. These are the isotopes or of elements that occur in nature. Those isotopes are radioactive, and some of them are radioactive, and humans have created thousands of other isotopes. And if you take the known isotopes, you'll find that you get a graph that shows you that the nucleus exhibits local minima in its structure. So this is a configuration where the nucleus is more stable than its surrounding elements. And if you look very carefully, you find that you have parabolas here. Those parabolas describe the process of radioactive decay, and all the elements that have been created by humans in particle accelerators, nuclear reactors, tend to reach the stability line, which are the isotopes that exist in nature. We'll have a very quick look at them in a moment. You'll find that if you plot the isotopes that I have shown earlier in nature, you get squares. If you plot the atomic number Z against the mass number, that's actually the neutron number N, isotopes that occur in nature tend to lie initially on a line that's 45 degrees if you follow the arrow here. So in that case, the number of protons is equal to the number of neutrons. Take an example, deuterium, one neutron and one proton. However, there is a tendency for the number of neutrons to increase compared with the number of protons. So there is a deviation from the 45 degrees line in favor of the an increased number of neutrons in the nuclei. So if you take uranium-235, you have 94 in that case protons, but 235 minus 94 neutrons, so there's a favor for a larger number of neutrons. Any particles that are generated by humans away from the stability line, if they have a larger number of neutrons, nature favors stability. So they turn internally one neutron into a proton, increasing the number of protons. So they move into stability towards the stability line, and a negative electron is emitted. And this is a process that we call radioactivity by beta minus emission. So a negative electron appears to be emitted from the nucleus. If we have isotopes that have a larger number of protons, you'll find that it tries to reach the stability line by decreasing the number of protons. So this occurs by the release of what we have seen in the cloud chamber photograph there, emitting the antimatter of the electron as a positron, or it grabs an inner shell electron from the surrounding shells around the nucleus. And this process is called the electron capture process. Through electron capture or through positron emission, the proton-rich nuclei try to reach the stability line. So in that case, the strong force is associated with the weak force in terms of radioactivity in general. You find that nuclides have different parities for their number of neutrons, number of protons, and total mass number. 160 them of the known nuclides in nature have an even N, even Z, and even A. 57 of them have an odd N, even Z, and odd and even A. 50 of them have an even N, odd Z, and odd A, and only 4 of them have an odd N and an odd Z, but an even A in that case. So in that, find that affects the stability of the nuclei. And as I suggested, nuclides that have an excess number of neutrons tend to be beta minus emitters in terms of radiation, trying to reach a stability line. Nuclei with a large number of protons try to emit a positron, which is a negative or the antimatter of the electron, or undergo electron capture, capturing an inner shell electron to reach stability in general. All right, so let us bypass the relativity aspects here and go to how to calculate those energy releases from nuclear reactions. And this is described as what's called the Q value of the reactions. And our ambition today is to learn how to calculate those Q values for different reactions in general. So we go back to our generic equation, like in chemistry, that we have a binary reaction. Binary means you have 2 particles interacting with each other as reactants, A plus B, giving me 2 other particles, C plus D, as products. Now we conserved already the charge, as we have seen earlier. We conserved the number of nucleons, and now we want to conserve the energy mass. Remember, mass and energy in our nuclear reactions are equivalent to each other. So in that case, if you carry on an energy balance, you have to say that both the rest mass energy, the MC square of the masses of the reactants, the rest mass energies, plus their kinetic energy should be equal to the kinetic energy of the products plus their rest mass energy also. Now, let us write this in an equation form. The rest mass energy is Einstein's equation for the reactants, AM sub AC squared plus its kinetic energy. Let's say it's E sub A. The kinetic energy of B is E sub B, of C, E sub C, and D, E sub C. So we're saying here that the rest mass energies plus the kinetic energy of the reactants should be equal to the rest mass energies and plus the kinetic energy of the products. And the energy release from the nuclear reaction is going to be the change in the kinetic energy. So we define it as Q as the kinetic energy of the products, C plus D, minus the kinetic energy of the reactants, which is E sub A plus E sub B. And in that case, what is the kinetic energy? What is the change in the kinetic energy? You'll find that from the equation here on top. You'll find that that is equal to the difference in the masses of the reactants minus the rest masses of the products. Now, it's very difficult for us to go and calculate kinetic energies as speeds of particles coming out in reactions. So we substitute that with our intellect. If I want to calculate the difference in the kinetic energy between the products and the reactants, I can also calculate that same value Q by the kinetic energies of the reactants minus the products. Notice here that's C plus D, but then here that's A plus B. So we define then in terms of practical engineering and scientific applications, the Q value as being the rest masses energies of the reactants, A plus B, minus the rest masses energy of the products, M sub C plus M sub D. And if these masses are in atomic mass units, we can extract them from the table of the nuclides and turn them into energy by multiplying by the square of the speed of light. Notice that in those reactions, we also conserve the charge. The charge of A plus B should be equal to the charge of C plus the charge of D. And in that case, for the Q value of the reactions, it's a difference in the masses of the nuclei, obviously, M sub A, M sub B, M sub C, M sub D. We have a problem though. In the table of the nuclides, we have listed the masses of the neutral atoms, meaning that's a mass that is measured in a mass spectrograph of the nucleus plus the electrons. And you'll find that in that type of reactions, which we call binary reactions, you can add to each one of those masses the masses of their electrons. M sub A has Z sub A electrons multiplied by the mass of the electron, and that would be the mass of the neutral atom. That these terms for the masses of the electrons cancel out. So in that case, we can go to the chart of the nuclides and get the neutral masses and be able to calculate the Q value of those reactions. That theory seems complicated, but in fact, it's very simple when we apply it to a very simple equation that you'll work on today as maybe an assignment. So let us look at a very important reaction between two isotopes of hydrogen. One isotope is deuterium, which is a hydrogen really because it has an atomic number of 1 and a single electron or a single proton. And another isotope of hydrogen that we call tritium, having also one single hydrogen, one single proton and a single electron. But here, the deuteron has an excess number of neutrons. So the mass number is 2, and the tritium has a mass number of 3 because it has 2 neutrons in its nucleus. But it's still hydrogen because the charge on it is 1 here and 1 here. When you combine those two isotopes of hydrogen at very high temperature, obviously, to overcome the Coulomb repulsion between the positive nuclei, these two isotopes of hydrogen combine together. They give you an alpha particle, a nucleus of helium, and they give you a neutron as an output. Now, this DT reaction is a reaction between isotopes of hydrogen. And in fact, these are the isotopes that are primarily used in the case of thermonuclear weapons, or what we called hydrogen bombs in the previous chapter. Remember the chapter on the nuclear world. In that case, deuterium or hydrogen can be releasing energy. So how much energy does it release can be obtained by calculating the Q value of the reaction. So we go to the chart of the nuclides. We find the mass of the deuteron in atomic mass units. We find the mass of the triton in atomic mass units. We find the mass of the neutron in atomic mass units and the mass of the alpha particle in atomic mass units. And it becomes simple now to calculate the Q value as the mass of the two reactants here minus the mass of the two products in atomic mass units. But we know that one atomic mass unit is equal to equivalent to 931.5 million electron volt of energy. So in that case, we can calculate how much energy is released from that hydrogen or DT reaction, as it's called, 2 here plus 3 with all the decimal points there. We cannot simply drop because the difference appears at the second and third decimal points. So we take as many decimal points as we can. So mass of deuteron plus the mass of the triton neutral atoms minus the mass of the neutron plus the mass of the alpha particle gives us a difference in atomic mass units of 0.0188 atomic mass unit. Each atomic mass unit is 931 million electron volt. So you'll find that that reaction here, the Q value of the reaction is 17.6 million electron volt of energy out of the reaction. So that is a fusion reaction that has been used, in fact, in thermonuclear weapons or hydrogen weapons. But in our future, we hope to be able to use it for the production of civilian and peaceful power that we call, of course, fusion energy. Notice that deuterium is an isotope of hydrogen. Our Earth is a water planet. So our water on Earth covers 70% of the Earth's surface. So we have ample supplies of deuterium as an isotope of hydrogen in the water in our ocean. So in that case, we can practically turn water into energy. So for an unlimited energy supply. I'll show you other reactions later on where you have deuterium fusing with deuterium. Tritium, though, does not occur much in nature, but we'll see that we can produce this from a reaction where a neutron interact with the isotopes of lithium, lithium-6 and lithium-7, and produce tritium for us, either hopefully for fusion reactions in our future. There are other nuclear reactions other than those binary reactions where you get 1D2 plus two reactants giving us two products. You'll find some reactions in the process of that, in that case, radioactive decay, where carbon-11 emits a positron and turns into boron-11. Notice here that 6 plus 5, 6 is equal to 5 plus 1, and 11 is 11 plus 0. Now, notice that carbon, the most common isotope of carbon in nature is carbon-12. So in that case, this is an isotope or a nucleus that has an excess number of protons. And as I suggested, it tries to reach stability as boron-11 by emitting a positive electron, and that is the positron, the antimatter of the electron. The interesting thing that we'll observe in more detail in the chapter on the weak force or radioactivity is that when you emit a negative electron, you emit another particle that we call an anti-neutrino. And in the case of the emission of the positron, we emit a neutrino, a particle that has a very, very small mass to the extent that it can penetrate the whole Earth's surface without interacting, but it is there for the conservation of momentum. If you consider if you ignore the mass of the neutrino and you use neutral atoms in that equation, the Q value is the mass of the carbon plus 6 minus 6 masses of electrons, because this is a nuclear reaction between the nuclei, minus the mass of the boron, and you subtract from the neutral mass you get from the chart of the nuclide 5 electron masses, minus the mass of the electron or the positron, because electrons and positrons are assumed to have similar mass. So in that case, you have to take into account the fact that the data that you have is for neutral atoms, whereas we have reactions in between the nuclei. The nuclear reactions, not atomic reactions. Notice that the reaction can be rewritten as the mass of the carbon minus the mass of the boron minus the mass of 2 electrons. So for that reaction to be positive, that mass here, the Q value should be positive, and that implies that the Q value should be larger than 2 electron masses. So for that reaction to occur, the masses of the particles should be, the difference in the masses should be larger than 1.02 million electron volt, which is the mass of 2 electrons. In fact, it is the mass of 1 proton, the mass of 1 positive electron and 1 negative electron, 1 positron and 1 negative electrons. As I suggested, when the nuclei have an extra number of protons, they tend also to undergo a process of electron capture. So you find the copper 64 isotope has an excess number of protons. It decreases it by grabbing an inner electron from the K shell of the atom, and it decreases its number of protons, with that proton interacting with the electron and turning itself into a neutron that remains in the nucleus in that case. So there are reactions that deviate from the binary case itself. And let's take another reaction here. A reaction that involves negative beta decay. We said that tritium is used in the DT reaction that is used in hydrogen devices, hydrogen weapons, or in our future now we are trying very hard to achieve fusion. That isotope of tritium contains 2 neutrons and 1 proton. It's unstable. So it has an excess number of neutrons, 2 neutrons and 1 proton. So in that case, you find that you can deduce, in fact, that it reduces its energy by emitting a negative electron. And if you balance the charge, 1 here should be 2 minus 1, and 2 here is the helium nucleus, and 3 should be equal to 3 plus 0. So the 0 here it's not 0, but it's a very small number. For the electron, it's 1/1800 the mass of the proton. But in that case, when you emit a negative electron, this is associated with the emission of an antineutrino by definition. And the antineutrino is identified with a star or a bar on top of nu here. This is the Greek n nu in that case. You'll find that the Q value in that case is the mass of the neutral atom of tritium minus the mass of the helium atom, helium-3 nucleus that is produced, because the masses of the electrons cancel out. So this is a problem when dealing with those reactions. Other reactions that occur also that involve the nuclei is the process of alpha emission. Some nuclei have so much instability, like uranium-235 and plutonium-239, that to reach stability, they emit a whole nucleus of helium. So plutonium-239 as an isotope, we mentioned that plutonium-239 was used in the initially in the Trinity test, and then later on in the device that was dropped on Nagasaki. Plutonium-239 that is produced by humans, it doesn't exist much in nature, emits an alpha particle, and lo and behold, something of great interest here as a trivia question, it turns into uranium-235. Why? Because the charge is conserved. You notice here 94 emits an alpha particle, 94 minus 2 is 92. That's the atomic number of uranium, and 239 minus 4 becomes uranium-235. So over time, the plutonium that we produce, if we don't burn it and produce energy, will turn eventually in nature into uranium-235. All right, so what did we observe about nuclear reactions so far? That first we conserve the charge, we conserve the total number of nucleons, we conserve mass energy. But there is another quantity that is conserved in those nuclear reactions. We also conserve momentum. And this is something that definitely come in from classical mechanics. Momentum is defined as the mass multiplied by the speed, if you do not include the vectorial quantities. We're going to use a very simple model here for how to use the conservation of momentum and what kind of information the conservation of momentum can give us about the strong force or nuclear reactions. We're going to assume that a particle interacts with the nucleus and both of them are at rest, that they form together in now a compound nucleus. So maybe you can get an alpha particle to interact with aluminum. They form a compound nucleus and then they split apart into two pieces that move in different direction. One of them would be C and one is going to be D. And because momentum is conserved in general in nuclear reactions, you find that the momentum of the C particle should be equal to the momentum of the D particle. Let's just gain some information here by squaring both sides of this equation, the momentum. So m sub c squared, v sub c squared should be equal to m sub d squared, v sub d squared. Let's separate the two m's here from m sub c here, n sub d, m sub d, and add a factor of 1/2 here and a factor of 1/2 here. What do you recognize here? Oh, this is the kinetic energy of C, and this is the kinetic energy of D. So the conservation of momentum tells me that the mass of C multiplied by its kinetic energy should be equal after the reaction to the mass of D multiplied by its kinetic energy. Now let us apply the conservation of energy, applying the Q value of the reaction. The Q value says that Q is equal to the kinetic energy of C and plus the kinetic energy of D. The A and B here are initially the nuclei were at rest, so that doesn't appear. So the energy of C, we have two equations actually here. If you want to look at it in more detail, you have two equations in two unknowns: kinetic energy of C and the kinetic energy of D. And this equation is a term of the Q value. So we use the elimination by substituting the kinetic energy of C being equal to the Q value minus the kinetic energy of D. And just substitute for E sub C as Q minus ED, expand it, M sub C Q here, and M minus M sub C ED comes to the other side. And lo and behold, we can calculate the kinetic energy of D as a function of Q and the masses of the particles that have interacted. And you notice that conservation of momentum is very interesting. It goes somehow against our intuition in that the Q value of the reaction is distributing itself in inverse proportion to the masses of the reactants. You could see here, this is the mass of C. The kinetic energy of D is equal to the mass of C, the other particle, divided by the sum of the masses. And if you simply substitute back in the equation, you can get E sub C in the same way is the Q value of the reaction in inverse proportion to the masses. So the light particle maybe gets more kinetic energy than the heavy particle. So that, again, I repeat that it goes against intuition. The energy release apportions itself in inverse proportion of the masses of the product nuclei. The light particle acquires more kinetic energy. So if you apply to the DT reaction that we worked on earlier, you'll do that as an assignment for other nuclear reactions too. You'll find that the neutron gets 17.6 is the Q value of the energy, but the energy is apportioned to in inverse proportion. So that's a mass of the other particle, the alpha particle divided by the two masses, the one for the alpha particle plus the neutron. this is an approximation where you should take maybe 4.123 and decimal points, but this is a very good indication. The difference is very small. So the neutron, which is a lighter particle in the D plus T reaction, carries 4 divided into 5. That's the same as 80 divided into 100 multiplied by 20 numerator and denominator, multiplied into the Q value. So the neutron from that fusion reaction of deuterium plus tritium gives us 14.08 million electron volt of kinetic energy. And the helium nucleus takes the inverse proportion of the energy. So that's 1 instead of 4 here. It gets 3.52 million electron volt. If you add those two numbers here, you get back 17.6 reaction. The exact values, if you take the exact decimal numbers here, is 14.06 and 3.54. The difference is at the second decimal point. So I'll ask you to balance some nuclear reactions, apply the conservation of charge, applies the conservation of nucleons, then apply the conservation of mass energy that gives you the Q value, and then the conservation of momentum gives us a way of figuring out how much that energy release, 17.6 million electron volts, apportions itself between the product of the nuclei. And this applies to most of nuclear reactions that we deal with, because many of them are really binary reactions, like deuterium plus deuterium, deuterium plus tritium, proton plus lithium-6, or a proton with lithium-7, and so on. And nuclear reactions are also exhibited in the fission process. In the fission process, we have a conservation of mass and energy, but the conservation of momentum doesn't work for us. So we just base our information on empirical type of observations. Let's take one of the very important reactions is the reaction of the fissioning of uranium-235. If you bring in a neutron and you absorb it in the nucleus of the isotope 235 of uranium, you'll find that even zero energy neutrons makes that new nucleus totally unstable. So the neutron added to the nucleus makes it unstable. It wiggles like almost like a drop of water. This is described as what's called the liquid drop model of the fission process. The drop of water has a charge. So the two charges electrostatically repel each other and they split apart, and basically they fission like a bacterium fissions into two new progenies of bacteria. And the same process happened in the fission process. You get two new elements in the middle of the periodic table, like here, that's krypton. That's not kryptonite, that's krypton as a gas, one of the noble gases, and barium. You notice here the atomic number 0 plus 92 should be equal to 36 plus 56. And the mass number 1 plus 235 should be equal to 97 plus 137. Plus, in the process, 2 to 3 neutrons are emitted in the process. One of them leaks out of the system. One of them is absorbed in another nucleus of uranium and emits some gamma radiation. And the third one, if it's 2 to 3 neutrons, it's 3 here instead of 2, can fission another nucleus. And the process can go on and on and on if you design it in such a way that out of the 3 neutrons, only one of them causes a new fission, then you can have a self-sustained chain reaction. In that case, to calculate the Q value, what we take is the masses of the neutron plus the uranium-235 minus the masses of the krypton, the barium, and the 2 neutrons, and that gives us about 200 million electron volts of energy. So if we take the equation here, go to the chart of the nuclides again, I'll give it to you as an exercise. You add the neutron mass plus the uranium-235 mass minus the mass of the krypton-97 in atomic mass units, the barium-137 in atomic mass units, minus the mass of the 3 neutrons, and you calculate how many atomic mass units difference. You notice that's 0.2 atomic mass units difference multiplied into the conversion factor from atomic mass units to million electron volt, and you get about 200 million electron volt of energy release. So the fission process can release for us 20 million electron volt per single reaction, whereas the fusion process for deuterium plus tritium can release for us 14.6 million electron volt of energy. Now, this is million electron volt. If you go back to the beginning of the page or the lecture, a chemical reaction produces only 4 electron volts or 13 electron volt. So in that case, look at this here. That is not 1 million times more energy release per reaction. This is 10 million times energy release per reaction. Actually, 100 million times if you consider a 2 electron volt of energy. So we are a factor of 10 million times per reaction more energy released from nuclear processes than it is from nuclear reactions. And this is really the humans having discovered fire, chemical reactions, electron volt levels of energy. When they moved into the discovery of nuclear reactions, the release of energy is 10 million times what it was initially with fire or chemical reactions in general. If you fission neutrons, you'll find that depending on the energy of the neutrons causing the fission, the products of the fission reactions differ in terms of their mass number in the periodic table of the element. If you start with neutrons that are thermalized, thermal neutrons, you get really some kind of a double hump distribution in the yield in terms of the mass number. So 2 elements in the middle of the periodic table. If you use high energy neutrons, that hump here is flattened out. These are 14 million electron volt neutrons from the fusion process. Obviously, the D plus T reaction, you don't get that prominent hump in the distribution, the yield of the elements in the periodic table of the elements. When you fission neutrons, something interesting happens. You'll find that the average energy of a fission neutron coming from the fission process is 2 million electron volt. So if you compare that energy of the neutron to the energy of the neutron that we calculated earlier from the fusion reaction, you'll find that fusion produces neutrons that are highly energetic, 14 million electron volts, whereas fission produces neutrons that have a low energy, which is only 2 million electron volt of energy. So that makes fusion neutron rich, but energy poor, because it produces only per reaction 17.6 million electron volt, whereas a fission produces 200 million electron volt per reaction. If you combine fission and fusion, you get an optimal process that we call a hybrid. So that would be a reaction that combines both fusion and fission, being more optimal in energy release than either fission or fusion alone. Some important aspect of the fission process is the release of what we call delayed neutrons. If the fission process was occurring continuously on the basis of the prompt neutrons, the neutrons that come from the fission process, our electrical engineers would not be able to build systems that can be controlled, because those reactions occur at the microsecond level, and control systems need some form of sluggishness so that you'll be able to control them. Luckily for us, you'll find that some of the fission products that come in after the uranium-235 or plutonium-239 nucleus fission, some of the isotopes like iodine-137 in that case, and bromine-87 emit beta particles that turns their nucleus into an excited state internally, and then one of the excited states emits a neutron. And same for iodine 137. You could see here that an excited state of the nucleus emits a neutron on a delayed basis. And that delayed basis takes, instead of microseconds, takes milliseconds. And that adds sluggishness. The system becomes sluggish. And in that case, we can build control systems that control the nuclear reaction itself. The fission process is governed by what we call the liquid drop model. Once you add a neutron to the nucleus of uranium-235, as you could see here, the neutron mass itself is distributed. Even if it's a zero kinetic energy, the nucleus becomes unstable. It wiggles back up and down and right and left. The charge here and the charge here repel each other into two nuclei. That's a symbol of fission. And through electrostatic Coulomb repulsion, they break apart and you get 2 to 3 neutrons released. So the same estimation of the Q value applies, but we cannot apply conservation of momentum in that case. You can read more about it, about the liquid drop model if you like. And this explains to us those parabolas that we have seen in the reaction. In the curve of binding energy, as you remember, we had some local minima and local maxima. And this is the frequency of the different isotopes in terms of the number of N or Z. You'll find that at the N, or the number of neutrons, Z is the number of protons in the nuclei. You get at numbers 2, 8, 20, 28, 50, 82, and 126 stable nuclei, and that corresponds to stable shells. You could see here, these are the stable isotope, it's called isotones number. You have a large number at those, what we call the magic numbers. In fact, it's 2, 20, 28. It's the same as the closed shells in the electronic structure of the atom. So the nuclei have a shell structure in the same way that the atom has also a shell structure. And as we suggested here in the actinium series of the table of the isotopes, in nature we have stable nuclei. This is a graph by the people at the Lawrence Livermore National Laboratory, and basically they show us an island here, the lead continent. Then some isotopes are slightly unstable, like thallium, uranium, and plutonium, but some people think that maybe in nature there is a shoal of deformed nuclei, and maybe in the same way that we have here heavy nuclides of uranium and thorium and plutonium, there is another island of stability, and this is the holy grail of nuclear physics today. People are looking into trying to discover those, maybe some stable elements, and maybe they exist in space, so spaceships can try to identify those elements. Something interesting about the strong force has to do with the cosmological inventory. What are we talking about here? It turns out that when we look at our world, our cosmos, our universe, you'll find that what we see as stars and dust among the star, what we call luminous matter, the star and luminous gas radiation, is only 0.4% of the known universe, only 0.4%. If you take non-luminous components like intergalactic gas, neutrinos, and supermassive black hole, that's 3.6% of the mass of the known universe. So if you add 3.6 to 0.4, that 4% is something that we can see in our known universe. Okay, just 6%, 4% here. So where is the 96%? The fascinating thing is that our knowledge is that because the universe is known to be expanding, you'll find that cosmologists suggest that 73% of our universe is dark energy in the expanding universe, and that there is also matter in the universe that we cannot see because there are no interactions happening there, and that's another 23%. So if you add those two, 96% of our universe is what? Dark matter and dark energy. And so all our knowledge about our universe is only that remaining, that's 96, 4% of our universe is what we know, what we see, what we learn in our class today, what you can learn in the libraries, in the books, reports, and the rest of it is still left to discovery in general. Some people suggest or speculate that is, I myself would think that maybe that dark energy is electromagnetic radiation. I proved to you earlier in the chapter that in the same way that mass can be turned into electromagnetic radiation or energy, the reverse can be occurring. So if we have radiation at a very high frequency, we derived that very simple equation with that R, capital R constant that tells us, all right, maybe this very high frequency radiation is the source of that dark energy and dark matter. However, people have other theories that suggest maybe sheets of filaments, possible parallel universes, electric currents made up by dusty plasma, plasma turbulence in the universe, plasma jets blasting from black holes at center of galaxies would be the source of the dark energy. And again, dark matter can be explained on the basis of that conjecture, in fact, that radiation can reverse itself from mass to radiation, but radiation can reverse itself into mass properties. So I put on the top here, possibly electromagnetic radiation. Some people call about the WIMPs as another type of a particle, weakly interacting particles. Some people talk about a possible universe, subatomic particles, local constant force, light absorption by hidden stellar dust, plasma turbulence in cosmic current filaments. And so basically what we want to say here is that 96% of our universe is still under investigation. So with great modesty and great humility, here is, we have learned a lot about the strong force exhibiting itself today as fission and fusion. But our knowledge about the rest of the universe is 96% lacking. So that opens up fascinating fields of inquiry and engineering and learning and science for all of our audience here today. These ideas are being investigated by satellites that are being launched into space. So for instance, there are in fact observations of dark matter. This is a picture here of the Milky Way taken from satellites. There is a thinking that the center of our galaxy contains a large black hole, but they think that the whole, our Milky Way and other galaxies are enveloped by dark matter, and that still needs to be investigated. The Chandra X-ray Stereoscope looks at the universe in the range of the electromagnetic radiation range of the X-rays, H nu. Remember, the energy of photons depend on their frequency. And this is another picture of NASA on a galaxy cluster. They gave it that funny name here, 1E0657-56. And they suggest that hot stellar gas is shown in red, and the dark matter here is shown in blue. As it suggests that we don't know what is that dark matter is yet. I suggest maybe it's electromagnetic radiation that has very high frequency, so it exhibits mass properties. This is a Hubble space telescope of a ring of dark matter in the galaxy cluster C10024 plus 17. And basically, I'll invite you to learn more by accessing this, the sites of NASA. What we are going to do at that point is learn that process by getting some assignments where you would carry on some of these calculations yourself, estimating the Q values and getting some practice on accessing the chart of the nuclei. I'll open here the chat room, and I still have time to go, so I'll start another chapter if you don't have questions in the chat room. Well, we want to use our time efficiently, so we go back to sharing the screen here. And let us look at another chapter. I want to minimize this. And what we can do is look at very quickly at radioactive transformation. No, let's go to the gamma rays interaction with matter. So what we dealt with today is a strong force. Gamma rays interaction with matter is the electromagnetic force, because we have seen that gamma rays at least can turn radiation into a mass. And this is what we have shown in the cloud chamber earlier, is a process that we call pair production. The pair here is a pair of electrons and positrons. But electromagnetic radiation interacts with matter through different processes that we'd like to cover in the remaining part of our lecture today. A reminder again is that the energy in electromagnetic radiation is described by Planck's constant multiplied into the frequency of the radiation, which is the same as Planck's constant multiplies into C divided by lambda. C is the speed of light, lambda is the wavelength. So long range radiation would have very low energy, and short length radiation has very high energy. And that's the case for X-rays and gamma rays as part of the electromagnetic spectrum. Again, here I bring to your attention this idea that in the same way that mass can be turned into energy, radiation itself can also be turned into mass. The process is reversible in general. We're going to bypass the relativistic treatment here and describe what are the processes by electromagnetic radiation interact with matter. That's very important for us, not in the range of lasers maybe or microwaves, but in the range of X-rays and gamma rays. The first process by which radiation can interact with matter is through what we call the photoelectric effect. The photoelectric effect is an effect that is very common to us. Like at dusk, you find that lights in the streets using what's called a photocell can detect the absence of light, and with the absence of light, the lights close a circuit and the lights in the streets go on. In that case, the photoelectric effect, by the way, the photoelectric effect was the effect that Albert Einstein studied to get his PhD. It was not relativity. He developed relativity later on. But the photoelectric effect is described by a photon, shown here by that wave, interacting now, notice that is an atomic phenomenon. It is not a nuclear phenomenon. It's interacting with an electron in the outer shell of the nucleus. And in that case, the energy of the photon, light or X-rays or gamma rays, is enough to knock off that electron of the shell in the atom. In that case, you end up now with an atom that has lost a negative electron So it becomes ionized, it becomes a charged nucleus. And this process is what we are going to call later on the process of ionization. The conservation of mass, the conservation of energy in that case, there is no mass conservation here, gives the atom a recoil kind of energy in an excited state, and you can conserve momentum in the x direction and y direction, but simply stated, it is measured in a way that is more like empirical in general. The photoelectric effect has a probability of interaction. We call it the microscopic cross-section. For the photoelectric effect, you could see here, it's proportional to the Z of the element, meaning that the atomic number of the element, the higher the atomic number, the more the photoelectric effect is exhibited to the power of 5. And inversely proportional to the energy of the photon. So this means that you'll find the photoelectric effect in situations where you have very high Z, like uranium has 94 as a Z, or lead, and very low energy of the photon. So if we describe the probability of interaction later on with the mass attenuation coefficient, you'll find that the photoelectric effect happens here at low energies of the photon. This is the case for lead, and at 0.01 or 0.1 million electron volt of the photon energy, the K-shell interactions of the photons, as you could see with the atom, are exhibited in the photoelectric effect. There is another effect that's very important, which we call the photonuclear effect, in that the photons can interact with the nuclei. I can, in fact, cause some fissions or some reactions in nuclei. So if you consider a very strong electromagnetic radiations in the form of gamma rays, emitters, isotopes of nitrogen-16, thallium-208, sodium-24, yttrium-88, actinium-228, emit very powerful gamma photons with a half-life of 7 seconds for nitrogen-16, with an energy of 6 million electron volts of the photon energy. That happens in boiling water reactors. We'll come to this when we study the boiling water reactor phenomena later on. You'll find that gamma rays can also be generated by very energetic reaction in particle accelerators. You can accelerate protons and let them interact with lithium-7, boron-11, or tritium, and you can get very powerful gamma rays, 17.6 million electron volts. So in that case, you can use this gamma photon, say gamma photons from radium, to interact with a metal like beryllium-9, and in that case, you can produce basically neutrons. So that becomes a neutron source for nuclear medicine therapy, or maybe for neutron radiography in general. So this is the photonuclear reactions. You can also, gamma photons or electromagnetic radiation can cause fission. So we call it the photofission process, and that if the photon energy is above 5.4 million electron volt, it can fission isotopes like thorium-230, uranium-233, or uranium-235. So here we have 3 processes already, but another process happens, which is called the Compton scattering. Compton scattering looks similar to the photoelectric effect, except that the photon has a higher energy, so it interacts with an outer electron, ejects an electron, so the atom is ionized, meaning that it's left with a positive charge, and the photon itself loses some of its energy. So you see here that a high energy photon with the short wavelengths shown here, losing some energy, so it has a higher wavelength. So this process is important, and it happens at intermediate energies and atomic numbers of the nuclei. So I'm going to show you the probability compared to the photoelectric effect. It is not Z to the 5th power or the 4th power. The Compton scattering is proportional just to Z. And here we can go real fast because we already studied another process of interaction of gamma rays with matter, which is the positron-electron pair production. If the energy of the photon exceeds the masses of an electron and the positron, we just mentioned that earlier in the previous chapter, you'll find that, oh, you turn your electromagnetic energy into mass, in that case, a positron-electron pair. And the probability of the interaction of the pair production is proportional to z squared. So the higher number of electrons, the higher the process of the pair production. Notice that the positron or antimatter does not exist in our universe. Some people suggest that there may be other universes that are primarily antimatter. So the positron finds an electron, they combine together and turns into electromagnetic radiation, the reverse process. The process is called the annihilation process. So matter and energy and becoming matter is two reversible processes. Electromagnetic radiation can also interact like light. In that case, the photon energy, the photon keeps its energy, but gives some part of its kinetic energy to the nucleus and gets it to recoil. So only the atom recoils. That happens with low energy photon, like the interaction of light with nuclei, and there is even the Thomson scattering. However, our concern is with the high energy photons, and in that case, we try to use the main processes, which are the Compton scattering, the photoelectric effect, and the pair production, to shield against radiation, because we learned later that gamma radiation or X-rays can interact with living matter, and if used to an excess, it can lead to deleterious effect. We have to use combinations of different metals to shield against radiation. If you get an X-rays, you are given a lead kind of a shield to absorb the different energies, because radiation, the electromagnetic radiation, has low probabilities of absorption at different energies of the photon. So they have what's called a transparency window for lead, that's 3 million electron volt, for copper at 10, and aluminum at 22 million electron volt. If you go back to the original graph that I have shown you here, you find that we can superimpose on each other the three processes of gamma, main processes of gamma ray interaction. This shows the probability of the photoelectric effect. This shows the range of the Compton scattering, and beyond 1.02 million electron volt, which is the mass of 2 electrons, you find that you get the pair production process. The three of them combine together, and you could see here that there is a minimum at the 2 million electron volt in the case of lead. This graph is for lead. So how do we quantitatively shield against gamma rays? You'll find something very interesting, that it follows an inverse square law, and you combine the three processes together, cross sections from empirical type of measurements. And if you have a beam of gamma radiation with an intensity I sub 0, you can decrease it to a level I sub x exponentially if you use a thickness x of these materials that contain lots of electrons, like lead, uranium, in fact, would be good too, or copper or iron. That n prime here in the argument of the exponential is the number density of the atoms in the material of density rho. So if you have a density of lead, 10 gram per cc, that is at n prime. It's a modified form of Avogadro's law. And when you multiply that by what we are going to call the cross section for the reaction, the total cross sections, you get what we call the attenuation coefficient. So in that case, the shielding against gamma radiation proceeds as an exponential factor. The interesting thing is that we are not really interested in I sub x here. We're interested in determining what is the thickness that would lead to an attenuation, or so that I of x over I naught is reduced to a certain number by a factor, maybe attenuation of 1 million times the intensity of the gamma rays, or 1 billion or 10 to the 10 for the reaction. Because we can get gamma producing reactions like the pair production process, we add to that equation what we call the build-up factor, which is the actual gamma ray flux divided by the flux obtaining the exponential attenuation law. So in that case, we use in the design of a gamma ray shield against gamma ray, shield against gamma rays, an inverse square law. This is an inverse problem of mathematical physics, like radar. You want to determine the distance between you and the plane, or a sonar, the distance between the ship and the submarine. So what you do is that you take the ratio of the attenuation that you want, you take the natural logarithm of both sides, and when you take the natural logarithm of e to the minus mu x, you get mu x. So you can solve for x in that case. And if you know the build-up factor b, and you take the logarithm of 1 over b I of x divided into I naught minus here 1 over the attenuation coefficient. I'll give you a problem. When you plug in number here for lead, you can calculate the thickness of the shield. That is more important to us. The I of x divided into I naught is the attenuation, or what we want in the shield. Gamma rays are becoming a very important topic in knowledge. Satellites have discovered that some gamma ray bursts occur in different parts of the universe. This is one of them observed. It's almost like supernovae, and those gamma ray bursts can be so violent and so energetic that they can sterilize our Earth, one side first and then the other side, if we are hit by them. So luckily, we haven't been hit by one of them. This would be an existential situation where extinction can happen. There are models of these gamma ray bursts that I'm showing here, discussing for you. It can happen if a plasma has a zero value according to the equations for electromagnetics or magnetohydrodynamics in general. Interestingly enough, it was discovered very recently that in thunderstorms, gamma rays or electrons do not just come into the Earth from lightning, but runaway electrons can be released to the upper atmosphere, and they are so energetic that they emit X-rays in the million electron volt region. So in that case, they are called gamma rays. So a new discovery is that in thunderstorms, stay indoors, because otherwise the gamma rays are affecting your body. And that was not known. Well, of course, you want to stay indoors away from the thunderstorm itself. New observations about electromagnetic phenomena are the transient luminous events. Thunderstorms will happen here between the clouds and the Earth in the troposphere. That's about 8 kilometers in height. But satellites and airline pilots have noticed other phenomena occurring with electromagnetic radiation. They call them the elves, the sprites, the blue jets, all of these above the in the upper atmosphere. So in that case, it's a subject for studies in terms of electromagnetic radiation. And this is a picture actually of blue jets. That is not lightning going to the ground. This is phenomena happening above the ground, and it's a topic for discovery. This is what's called the sprite from the tops of thunderstorms. It's all electromagnetic radiation in general. All right, the gamma ray bubbles occurs also, and that's what I'm trying to show you is the thinking is that the center of our galaxy has a black hole with 2 gamma ray bubbles on top and the bottom of it. So I'll give you a small problem here in shielding with lead, water, and concrete, and just apply the gamma ray equation. And you should expect to know what are the methods of gamma rays interaction with matter. And I'll close it at that. It was a long lecture, but we covered 2 chapters in our class. Have a nice afternoon, everybody, and the class is dismissed. I'll be open for questions, and let's stop the recording here.